We're going to go through some conceptual questions here. All of these questions are going to be related to Faraday's law and Lenz's law. Faraday's law, if you recall, is the equation that describes how to find the EMF induced when the magnetic flux is changing. Lenz's law is the one that tells us that induced current is always in a direction that opposes the change in flux. So here is our first question. Try answering that on your own first. So the correct answer here is B. So the magnetic field that they've already drawn in the picture is a magnetic field created by something else. It's not the magnetic field created by the loop. I don't necessarily care what is creating this field, but this is what we would consider an external magnetic field. Something else is creating it. Our loop, this circle here, is being pulled into this region where the magnetic field points into the screen. To determine direction, our first question we need to ask ourselves is the magnetic flux changing in this situation? Well, if I consider the loop getting more and more inside, it's going to encompass more and more of this external magnetic field. So the answer to this is yes. The flux is changing as that loop moves into this region. Number 2 was to ask ourselves, is the magnetic flux increasing or decreasing? Is it getting bigger and bigger or smaller and smaller? Well, as this loop moves to the right, it is taking and allowing more of these magnetic field lines to point through. So in this particular case, the magnetic flux through the loop is increasing. And we're just looking at the moment in time or the period of time where the loop is entering this magnetic field. That's what the problem is specifying to us. So we're just accounting for this loop entering the magnetic field. We know this loop, as it moves into the magnetic field, is going to have more and more magnetic field lines moving in. So the flux is increasing. If the flux is increasing, then the induced magnetic field by the coil or loop is in the opposite direction of the external magnetic field, the one it's moving through. So in this specific example, since the flux is increasing, the loop is going to create its own magnetic field that points out of the screen. Because that is opposite the external field that points into the screen. It's trying to decrease the flux back down to what it was before. Okay, so our loop, I'm just going to draw a loop down here. We need the magnetic field in here to point out of the loop. Since this loop, the current can only flow clockwise or counterclockwise around this loop. The right-hand rule, we make our thumb or point our thumb in the direction of the induced magnetic field. So in this case, we know the induced magnetic field needs to point out of the screen. So point your thumb at yourself and make sure it's your right hand. If my thumb is pointing at me, my fingertips are curling this way. That means the induced current is flowing counterclockwise around this loop. That's where we get B as our answer. So again, a multi-step process. So thinking through whether the flux is changing, how it's changing, if it is, and then the direction of the induced field that we need, and then our right-hand rule. So let's look at another one. Okay. Excuse me, I'm going to drag to the next question, and I apologize. I know the size of everything's changing. I don't know why my computer decides to change the size, but here we go. Next question. The correct answer here is C, none, meaning there is no induced current. The reason why is as this loop moves, the loop's area is not changing size. It's still in the region with the magnetic field. So the magnetic flux is constant. If the flux is constant, then there's no induced voltage or induced current that occurs. So there will be no induced current in this case. Here is another question. It's a little bigger so you can see the picture better. The correct answer here is A. Now, this field is constant, uniform. So the flux is not changing because of a changing magnetic field. It's changing because the area is changing. Magnetic flux, B dotted with A. Since the area is changing with time, the flux is changing with time. In this particular example, the area gets smaller. That means the magnetic flux gets smaller, meaning it decreases. So since the flux is changing, there will be an induced current. When the flux decreases, the induced magnetic field by the loop is in the same direction as the external one. So as the external magnetic field. So coming back to our picture, our external magnetic field points into the screen. That's labeled there. We also want an induced magnetic field into the screen. Same direction to try to increase the flux back up. So, right-hand rule. Point your right thumb directly towards your screen, as if you could push your thumb into the screen. When I do that, if my thumb's pointing into the screen, my fingertips are pointing this way. My fingertips of my right hand represent the direction of the induced current. And so that's why we get clockwise in this particular case. Let's look at one more. The correct answer in this case is A. So similarly, we need to know if the flux through our loop is changing. So our loop is this rectangle up here. This loop is not connected to a battery. It's not connected to a power source. So the only way it would have current flowing through it is by way of induced current. So flux changing. The reason this loop up here has a changing flux is because this bottom wire is creating magnetic fields around it. And those magnetic fields, if I put my thumb in the direction of current, my fingertips show me which way the magnetic field circles that wire. Ultimately, what that means is B of the wire up here in the region where the loop is located points into the screen. This B of the wire is the external magnetic field. We know the strength of the magnetic field due to a wire depends upon how much current is flowing through it and how far away, so D, how far away from the wire we're talking about. In this particular case, the problem tells us that the current in this wire is increasing with time. What that means is that the magnetic field it's creating is increasing with time. Well, the loop has magnetic flux that depends on B of the wire and then passing through the area of the loop. Technically, to calculate this, we would need to integrate because the magnetic field from the wire would be stronger at the lower points, closer to the wire, and weaker at the points closer to the resistor because that's farther from the wire. But we're just asking about the direction of the induced current. So we don't have to actually solve numerically anything. What we do need to recognize is that the magnetic flux through the loop is increasing. This is the important piece here. Number one, it's changing. It has to be changing to have that induced current. To determine the direction of the induced current, I have to know how the flux is changing. So I know the flux is increasing. That means the loop will create its own magnetic field. We call this the B induced, that points opposite, not whatever that word is, that points opposite the external field. So as we've already mentioned, the wire is creating a magnetic field within that loop that points into the screen. So the induced magnetic field points out of the screen. Once we determine that is when we can do the right-hand rule. So I'm just going to draw my loop again over here. Here's my loop. I need the magnetic field induced by the loop to point out of the screen. So my right-hand rule, I need to take my thumb of my right hand and point it towards me, out of the screen. As if something is jumping out of the screen at me. I point my thumb at me, out of the screen. My fingertips represent the induced current direction. So with my thumb pointing at my face, my fingertips are pointing like this around my thumb. That means the induced current is flowing counterclockwise through this circuit, or through this loop, I should say. The specific question is the direction of the induced current through this resistor. Well, the current can only go right to left or left to right. My arrows are pointing this way, and that's why our answer is right to left. The current's coming from the right side of the wire, flowing through the resistor towards the left side of the wire. So induced current, multi-step thought process based off of whether the flux is changing and how it is changing.